Well, this week we have the pleasure of having some video lectures instead of meeting in class. There's been a lot of people that haven't been showing up for class anyway. So they'll be able to get a lecture instead of just looking at the notes. Well, what I want to talk about, we're shifting now from looking at the diversity of sharks and skates and rays, from looking at how they're classified and the different groups that they are. From now until the end of the semester, there's going to be a lot more focus on individual aspects of their biology, biochemistry, morphology, physiology, reproduction, these types of things. That it's not going to be so much memorizing what all these different groups are. It's going to be gaining an appreciation for how they've managed to be around for 400 million years. And then towards the end, look at the problems that this lifestyle causes for these sharks in terms of their populations being sustainable. So the first of these topics is locomotion. And obviously, most of these sharks and skates and rays get around, they move around. Locomotion is important for prey capture and predator avoidance, a number of different things. So these are the 6 topics that I want to talk about in terms of locomotion. This lecture probably be about 50 minutes, but since it's a video lecture, it doesn't really matter how long it takes. It could be 55 minutes or it could be 45 minutes. When we're done, then we'll be done. So we're going to talk about movement through the water, first of all. Obviously, it's a different matter to move through water than it is through the air. There's some disadvantages for moving through water compared to air, and there's some advantages for moving through water compared to moving through air. So most of these animals, especially some of them, they're highly mobile. Some of the fastest things in the ocean, mako sharks, and they travel thousands and thousands of miles, and all kinds of different aspects of their biology focus on movement. They have got to be able to move. So that's what we're going to look at. How do you move through the water? What kind of physics does that take into consideration in terms of advantages and disadvantages? And how does it influence how these sharks and skates and rays are designed in terms of things like their scales and their fins and their tails? And then also what kind of scales that they're moving on, or if you put all those different things together, what their bodies are actually moving like in order for them to propel themselves forward. So first of all, why do you need to move? If you're a big enough animal on land or in the water, it's very, 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 very common that you move. You have some means of locomotion. Animals, other organisms had developed locomotion millions and millions of years ago, probably billions of years ago maybe, some mechanism for moving, because it's important to move to enter new habitats, to find food. It's important to move to avoid predators. It's important to move sometimes to find an optimal environment for your young versus where you're an optimal environment for feeding. And, part of the environment is dynamic sometimes. It gets too cold, it gets too hot, it gets too little oxygen, too much something, low pH. So if you can't move, then you're stuck and you're subject to whatever the environment is like. But if you can move, then you can get up and go and move yourself to some more favorable environment. It's very important for being able to survive. One of the things we're going to see, sharks, skates, and rays, that they don't all need to swim all the time. There's a lot of them that lay on the bottom. Obviously, the rays and some of the sharks are very bottom oriented, and their lifestyle is a lot more towards laying on the bottom than moving, but still at some point they move, they get up and move, whether it's a long distance or not. So it's very energetically expensive to move through the water. This metabolism, burning fuel and using it towards movement is what takes a lot of energy, uses a very large proportion of the energy that's consumed in order to move. Muscles contracting use a lot of oxygen, use a lot of ATP. It's an expensive thing to move. It's worth it, obviously. Evolutionarily, there's been some trade-off that's favored movement over not moving. So the rewards outweigh the costs. However, there are costs. If you think about some of the advantages of being in water compared to air, well, one is that there's a lot of support. There's a lot of animals in the water that are very flabby. If you take them out of the water and just have them in air, then there's nothing to support them. Some of them don't have a skeleton, or some of them have skeletons that are very flabby. And so living in the ocean or living in any kind of water allows you to be a lot bigger with a lot less muscle mass and skeletal mass and things like that. Whereas when you get onto land, then you can collapse because you're so much heavier. The forces of gravity are so much greater in air than they are in land. So there's some advantages of it. And also, if you're in the water column, it helps you to avoid sinking. Your big body, or even your little body, a body resists sinking. The forces of water help you maintain your position in the water column, which for a lot of animals, again, for that, the physiology, maintaining a certain position in the water column so that you can find enough to eat, so that you can avoid predators, so that you can avoid water that's too hot or too cold or too much pressure. It's important to be able to maintain your position in the water column. And being in water as opposed to air helps. It's easier to maintain your position vertically in water than it is in air. And so what you see, if you look at a whole bunch of different sharks and skates and rays and marine organisms, aquatic organisms in general, is that there's this advantage for being in water that you can float, you can stay afloat, you can maintain your position in the water column with not that much energy. You don't have to expend that much energy. So another thing that we're going to see, not so much in this section, but the next lecture, is that it's very common for marine organisms to store some kind of low density matter in their muscle, liver, bones, underneath their skin, wherever it is. An obvious other answer to that challenge is having a swim bladder, but sharks and skates and rays don't have swim bladders, and there's a lot of animals that don't have swim bladders as well because they move up and down the water column too quickly, or because they're at depths where having some kind of gas-filled bladder is not going to work because the pressure is too high. So this idea of having some kind of a low-density matter is very common. Well, let's talk about this, the cost of locomotion. If you're going to go from point A to point B in the water, what kind of energetic costs are you talking about? Well, if you're moving through the water, muscles contract, it bends your body back and forth, and it moves your tail back and forth through the water, and it generates some propulsive force. So muscles have to contract in order to move you forward. And if you look at how muscles contract by shortening, these muscles, protein filaments in the muscles slide past one another. And so if they shorten at different speeds, then they're producing different levels of force. So if they're shortening quickly, they're producing a lot of force. If they're shortening more slowly, then there's more force per contraction. If you think about the distance that these muscles are contracting as well, in a big animal, the distances that the muscles are contracting are actually more because they're bigger. than some little tiny animal where the muscles aren't contracting very much, the force that's generated is a lot less in a smaller animal than a big animal. So big animals, when their muscles are contracting, of course, the speed of contraction has influenced how much generated, how much force is generated, but so is the size as well. And so if you take this into consideration, how much energy does it take to move a certain distance? With muscles contracting, the speed of muscle contraction, and the force that's generated from muscles contracting in small muscles versus large muscles, then what you find is if you measure the amount of energy per unit distance, so it takes, this is also based on the relative size of the animal. How much energy does it take for something to move from here to there? Well, if you look at the force of muscles contracting and the amount of propulsive force that's generated, then what you find is that bigger animals can move the same distance as small animals, expending less energy. It's not an absolute less energy, but it's less energy per unit distance, per unit weight. So for instance, if you've got a big animal and you're measuring how much energy per unit weight it takes for that animal to move 100 meters, it's going to be less in a big animal than it is in a small animal. Small animals and muscles are contracting a shorter distance, generating less propulsive force. And if you express that on a per weight basis, then big animals can move the same distance as small animals with proportionately less energy. So that's what this figure shows you. The energy cost per unit distance to go 100 meters is less. It declines as animals get bigger. So there's an advantage for being big in terms of moving. Of course, if you're big, you have to move more. I mean, it takes, if you measured the amount of energy, just the energy itself, then of course a big animal would be using more energy. But if you express that as a per unit weight, then it's a relatively less energy than a small animal. So what are you experiencing if you're moving through the water? You're experiencing drag. If you think about moving your arms, waving your arms in the air, it's very easy to do. There's hardly any resistance to you moving your arms. But if you think about moving your arms in the water, now that you have to displace all these water molecules, you certainly can't move your arms through the water nearly as easily and nearly as fast as you can move them through the air. It's a lot easier to move something through the air than it is through the water. So there's some advantages that we looked at before for being in the water, but there's also some disadvantages. There's advantages for your skeleton, and there's advantages for avoiding sinking, but there's disadvantages in the drag that you experience moving through water compared to air. So the forces that you have to overcome to move through the water are drag forces, different types of forces of drag. So that's what we're going to look at, and you'll see when we're done with this that there's different shapes, different body shapes, different means of propulsion, different aspects of the surface of these sharks and skates and rays that are related to drag. Some of them minimize drag, and some of them don't really care about drag when they move. They don't move that often, or being very efficient swimmers isn't such a big deal. They're a lot more benthic oriented. They get up and swim every once in a while, but they're not constantly swimming. So we're going to see a lot of variation in drag, but drag is the force that has to be overcome to move through water. And look at some of these things that influence how much drag there is. What is the viscosity of the water? A lot of the water in the ocean is the same density, but if you're swimming through water of different densities, it's going to impinge different amounts of drag on you. Body shape is important in creating a lot of drag or minimizing drag. You're going to see there's a very efficient design body shape in terms of moving through the water. And there's other body shapes that aren't very good at moving through the water. Another thing that's important is the surface area of the body. Surface area of the body is what's in contact with water. That's the part of the body of these animals that are having to move those water molecules apart. They're experiencing friction from moving through those water molecules. The middle of their body, in the core of the body that's not touching water, that's not experiencing drag like the body surface. And another thing that influences the amount of drag is the speed, the velocity at which you're moving through the water. Okay, so let's look at this drag, the forces of drag, and what animals do to reduce drag. Well, there's two main forces of drag. You can pause this and look at this in more detail than I'm going to talk about. But there's the force that has to be overcome is inertia. You're stopped, and you've got to start. It takes a certain amount of energy to get going in the first place. That's a force that has to be overcome. If you're swimming all the time, then you don't always have to deal with that. But drag is resistance to movement through air or movement through water. In this case that we're talking about, you're moving these water molecules apart. These water molecules are touching the surface of your body, and they're resisting you moving forward. So in terms of the water itself, we talked about viscosity, how thick the water molecules are, how easily they move apart. And then density is another thing that it's related to viscosity, or viscosity is related to density. How dense is the water that you're moving through? In terms of the animals themselves, there's factors about the animals that influence how much drag they experience. One is the surface area. The bigger the surface area is, the more contact there is with water molecules, the more drag there's going to be. And the other thing is the velocity. The faster you go, the more drag you're experiencing. Two things that are also very important, where there's a lot of variation in these sharks and skates and rays, is the body shape and the accessories that are sticking out. There's accessories that can minimize drag, creates turbidity, or it reduces the amount of turbulent flow around the body. There's a number of different things. So we're going to look at body shape first of all and see that there's this ideal shape. If you were a physicist, if you were an engineer and you're going to design some hydrodynamic shape that would move through the water with the least drag, you could come up with a shape that moves through the water efficiently. And it's similar to the shape of fast-moving sharks, skates, rays, at least sharks anyway. It's similar to other animals as well. And then these accessories. There's a number of accessories that minimize drag. So there's a number of different forces, as I mentioned. We're not going to get into all these different things, but there's pressure differences between the front and the back of animals that can be minimized by certain shapes. There's pressure drag that's maximized by certain shapes. So if you've got a round object that moves through the water, there's not much difference between the front and the back. If you've got kind of a rounded head and it tapers off to the back, then there's a big pressure difference. If you've got that kind of body shape where it tapers off in this fusiform shape, reduces the amount of pressure drag. There's also form drag, where all these water molecules you're pushing out of the way, and there's frictional drag. It has to do with the surface area, the skin that's in contact with these water molecules that are slowing your movement through the water because of friction that you're experiencing. So the point is, not to get into all the different physics, but there's different types of drag that an animal experiences when it's moving through the water. You can modify the shape of an object that's moving through the water and you can minimize pressure drag. You can minimize form drag, especially if you change the shape of your body. And then in terms of frictional drag, you can minimize that by the surface area. You can minimize that especially by these different appendages, special structures that are on the surface of an animal. So that's what we're going to look at. And if you look at this figure over here with the drag coefficient, then there's this sphere has a very high drag coefficient. That means there's a lot of drag when it moves through the water. Some of these substances, the cube is very high. And if you get down here, here's a short cylinder, is pretty high. You get down here to this, look at this streamlined body where the front is big and it tapers off to this shape in the back. It's like a teardrop kind of. Look how low that drag coefficient is. This is a shape of an object that will move through the water efficiently. And as we'll see, that's a common shape that you find in a lot of sharks, tuna, dolphin, penguins, turtles. It's a very common shape, especially for organisms where it's important for them to minimize drag, and it's important for them to maximize the efficiency with which they move through the water. So how does that drag relate to body shape? If you have this teardrop shape where there's a pressure difference between the front and the back, then that reduces drag. So a teardrop shape, that's what you find in some fast swimming sharks, that's what you found in some dinosaurs, that's what you find in dolphins, that's what you find in tunas, that's what you find in penguins. So it's and some turtles. It's a very common shape for animals that are maximizing the efficiency with which they move through the water. There's been this convergent evolution towards this body shape amongst different animals that aren't very closely related to one another. If you look at fast swimming things, they tend to have this fusiform or teardrop shape. So at this point, this teardrop shape, you find it in marine mammals and fish and sharks, even in squid and birds and reptiles. It's a very common thing, and it makes sense because it reduces drag. There's a minimum drag that's related to that type of shape moving through the water. Well, in terms of these accessories, how do you reduce this frictional drag? Got all this water that's in contact with the body. Well, one of the things that you can do is minimize the turbulence that your body's experiencing when it's moving through the water. You can direct the water flow away from the body surface and move that water along your body efficiently. That's exactly what these placoid scales of sharks do, or these dermal denticles. They have little grooves. If you look at this picture up here, you can imagine water being directed through these grooves. It's like a flow direction that's directing the flow of this water along a very direct pathway, reducing the amount of turbulence that there is in the back here, creating this less drag. And so you've got all these different sharks and skates and rays that have these dermal denticles that they don't just have any shape for protection, but they've got this very distinct shape on a pedestal that lifts it up above the surface of the body and directs water along this flow. And it minimizes drag and increases the efficiency which they move through the water. And so people have tried to replicate this. There's a lot of biomimicry that's been done. There's Michael Phelps with his suit that has these dermal denticles. And they're artificial ones, but they're based on the same principle that you can minimize drag, maximizing the laminar flow of water around your body and reducing this frictional drag. So it's not anything, it is naturally occurring in sharks, but it's something we've tried to take advantage of for swimsuits, for submarines, minimizing the amount of drag and maximizing the efficiency of, you can imagine, a ship or a boat or a submarine moving through the water. Not just reducing noise, but reducing the amount of energy that it costs to go a certain distance. Here's some more accessories. If you look at a lot of fast swimming fish, including sharks, they've got keels, they've got finlets, they've got scutes. They've got these appendages that are right in front of the tail. And as these move through the water, they displace the water, they break up the water. And what comes right after these little appendages, the finlets or the keels or the scutes? The next thing to pass through that water is the tail. And the tail is beating back and forth, back and forth. And so the tail is beating through this water that's just been disturbed by these finlets or scutes or keels. And so the tail can move through this water with less resistance. And so it takes less energy to move your tail back and forth. There's still propulsive force that moves you forward. And so if you look at this figure here, here's this fish that doesn't have any scutes or finlets or anything. It's moving through this turbulent flow. Here with these finlets, then the direction of the water, the amount of turbulence is reduced, and you have the fin moving back and forth through that kind of water, as opposed to this. You can generate greater forward propulsion with less energy by having all these appendages. So if you look at fast swimming tuna, fast swimming sharks, fast swimming relatives of tuna, other fish, they tend to have a lot of these types of appendages, whereas more slow moving fish don't. They don't need them. They're not trying to maximize the amount of energy. All right, well, let's look at these two, hydrodynamic forces and propulsive forces. Now, these are two different things. Hydrodynamic refers to movement through water. You're moving through the water. Hydro, water. Dynamic means that you're moving, as opposed to hydrostatic or aerodynamic. And then these propulsive forces. If you look at the fins of sharks, and if you look at the body of some of these sharks, then it's in a way similar to airplane wings. Airplane wings, it's again this pressure difference, not so much between the front and the back, but the top and the bottom. If you look at the shape of an airplane wing, then it's got a different shape on the top than it does on the bottom. On the bottom it tends to be flat, on the top it's rounded. In the front it's more broad, and in the back it tapers off to this narrow shape in the back. So what happens when air flows across these wings is that the air moves faster across the top of the wing than it does across the bottom, and there's this pressure void, and the pressure force lifts the wing up. That's how wings work in terms of moving through. It's the same thing with fins. If you're moving through not air this time, but water, and there's this faster moving water on the top and slower moving water on the bottom. There's a high pressure, low pressure difference, and there's lift that's provided. So if you look at the fins, especially the pectoral fins of sharks, they tend to be more broad in the front. They narrow, taper off in the bottom, and they tend to be rounder on the top surface than on the bottom surface. You look at the head and the body of some of these sharks. The entire body of these sharks has a similar type of shape as a wing, or an airplane wing, or a fin. And then in terms of the tail in terms of providing lift, it's another question. A tail can move through the water and also provide some lift, but it's mostly the lifting surfaces that when this tail provides this propulsive force, which is what we're going to talk about now, then these objects that are moving through the water, like the fins and the head, are generating lift, hydrodynamic lift. Well, as the tail moves through the water, it's kind of a complex idea. You've got this heterocercal tail where the upper lobe is bigger than the lower lobe. If you're looking at a little fish with the upper and lower lobe, as it beats back and forth, these are the type of propulsive forces that are generated. And the tail, of course, is beating back and forth, so you have this back and forth as the muscles contract. That's the kind of propulsive force that's generated. With the tail, it's a little different, where you've got this upper lobe and lower lobe that are beating back and forth at different velocities. They're creating different forces, but for the most part, it's a little lift, but there's this propulsive force that moves a shark or a skate or a ray, if they have a tail like this, some of them do, besides the sharks, then they're creating this propulsive force that moves them forward. So you need some propulsive mechanism. If you look at fish or squid, or crustaceans, there's a whole bunch of different ways that animals generate forward propulsion. With sharks and skates and rays, there's some. They can fly through the water. They can move their pectoral fins through the water. But of course, the most common thing is them beating their tail back and forth and creating this forward propulsion that's going to move them through the water. And if you're big, you can generate this propulsive force and do it more efficiently than if you're small. If you're small, it takes more energy per unit weight than if you're big to move the same distance. Well, the last thing that I want to talk about today then is these different types of swimming modes. There's some different ways. It's basically how you beat your tail back and forth. There's some sharks that move very quickly. There's some sharks that move very slowly. There's some sharks that bend a lot of their body and other sharks that don't bend very much of the body at all. So in terms of swimming modes, this is true of fish in general. You've got these different swimming modes. You can be anguilliform, which refers to eels. So basically you're swimming like an eel, or similar to how a snake crawls along the bottom. Your entire body moves back and forth. And so you've got some sharks, like the blue shark, for instance, that's very long and skinny, and they swim kind of like an eel with this type of movement. You've got the subcarangiform, where you may have sharks that are somewhat benthic oriented, but they're moving around quite a bit, and they're not swimming fast all the time. They might be intermittently swimming fast, but they're not swimming particularly fast. And if you look at what happens to the head of a subcarangiform, their head is going back and forth about that much, and then their body is bending a certain distance up with their body. About a third of their body is bending in the rear, so it's not quite S-shaped so much like an eel, but there's quite a bit of wiggle back and forth. And then you've got carangiform, where their head is doesn't move a whole lot, but it moves somewhat. And then you've got about a third of their body, maybe a little more, moving back and forth. You've got these carangiform type of movements that aren't so common in sharks. There's a lot of sharks that move like this. Their head moves back and forth, dealing with their blind spot as well. And then you've got some species that have this tuniform type swimming, which is like tuna. Tuna do this. If you look at the amount of head wiggle back and forth, it's very small. And basically, if you watch this animal swim, whether it was a shark or a tuna, it would only be the back third of their body, maybe not even that far, that's moving back and forth. The whole rest of their body, 75% or 70% of their body, is very straight, and it's just this little engine back here that's going back and forth very fast, generating a lot of forward propulsion. And they're not, the side of their body isn't experiencing drag like the side of these. When they turn sideways, drag is being produced because it's hitting against the side of their body. Well, another way that you could look at swimming is not so much what their body is doing, but more behaviorally. You're swimming along. Are you swimming all the time and never stop? Do you swim for long periods of time and rest in between, or you swim fast for certain amounts of time? But you're not the fastest thing out there. You have prolonged swimming, but not necessarily sustained swimming. Or maybe you lay on the bottom a lot, and the only swimming that you do is when you get up off the bottom and go, sometimes chasing prey or avoiding predators. In that case, you expend a lot of energy to move a short distance, and then you stop again. You rest. So you could look at sharks and skates and rays in that respect. You've got sustained swimming, you're swimming all the time. You never stop swimming. You're obligated to swim. And then these other ones where you're either swimming less, maybe sometimes for a long period of time, but there's other times when all you're really doing is cruising around, not expending a whole lot of energy. Or you have a minimal amount of swimming and a lot of resting, sometimes even on the bottom. Okay, well, let's look at this sustained swimmer. You've got these, they never stop. They're swimming all the time, swimming, and they've got a special physiology and biochemistry, circulation, enzymes, all these. We're going to look at this next week, or later this week, actually. So these species can swim fast, basically without getting tired. They don't experience muscle fatigue. They can use oxygen. There's a lot of oxygen that's delivered. They've got a number of different mechanisms for swimming fast, and swimming fast a lot of the time. I mean, that's what they do. Is they're swimming around very quickly. Mako shark, salmon shark. Then there's this prolonged swimming. You've got other species that they don't lay on the bottom. They don't stop swimming. They have to swim, and they do swim. They're obligate swimmers. However, they swim fast for shorter periods of time, and if they swam fast, they don't have all those physiological mechanisms that mako sharks have to avoid muscle fatigue. They use up their oxygen. They start producing lactic acid. They have to recover, basically, from prolonged. If they're swimming very fast for very long, they're going to get tired, and they're going to have to rest, and they're going to have to replenish their oxygen and energy supply. So they can swim for short periods of time anaerobically, but then they have to repay that oxygen debt. So there's the whale shark, and there's the hammerhead. These type, very common. Then you've got these burst swimmers that are laying on the bottom. They're very bottom oriented, and they get up off the bottom and they swim short periods of time. But it is very bursts of energy rather than constantly swimming, and certainly not swimming long distances very efficiently. That's not their mode of life. It's not their swimming mode, if you're looking at in terms of their activity type patterns. Then you've got this other type with skates and rays, where there's some of them that flap their arms up and down, basically. And there's other ones where there's a wave that moves along their pectoral fin. And then these chimeras, which are relatives of sharks, although we have barely mentioned them, they have a combination of ways of moving. Anyway, there's a lot of things that aren't sharks that are in this group that we've talked about this class, and they move. Of course, they're not. Some of these are doing this sustainably, but if you're a ray or a skate, that kind of shape, then obviously you're not generating propulsion from your tail for the most part, but you're generating forward propulsion from your wings. You're flying through the water as opposed to generating forward propulsion with some kind of engine in the back. Okay. So that is the lecture that I wanted to give on locomotion. It's obviously very important in sharks and skates and rays to be able to move. And there's some that lay on the bottom and get up and move sometimes. There's some that are swimming all the time. There's some that are swimming faster than anything else in the ocean, really. Nothing is faster than them. So there's a lot of variation in terms of how they swim. There's a lot of considerations that go into the type of body you have, the type of appendages you have, accessories you have related to your lifestyle. Are you swimming all the time and minimizing drag, or are you bottom oriented, and so you don't need those kind of appendages and accessories, and you don't have to worry about what your dermal denticles are like. So here's this oceanic manta ray, the giant manta, is all over the world. Pretty common. They get to be really big. If you see these out there, I mean, they're huge things, and they're flapping their wings through the water, filter feeders going along. They do a lot of loops and circles, and there's places where you can go and swim with them. Off of Hawaii, down in Mexico, you can jump in the water in Hawaii. Off of the Big Island, there's this place where they have the spotlights in the ocean, and attracts a lot of plankton. And then you go and you dive, and these big giant manta rays swim in there, and so you're diving amongst the manta rays coming there at night. It's quite spectacular. And there's other places where they're there filter feeding, sometimes along with whale sharks, a lot of whale sharks and these big manta filter feeders. And so they're really interesting. I think somebody has given a presentation on this, so I don't want to say too much about the giant manta. So that's the first lecture.